Lesson 12.4. We're still talking about probability, folks. That is the name of the game this whole chapter. So we're not going, that probability is not going away. Probability distribution. So we're going to look at how probability is split up in a setting. Okay, that's our probability distributions. So let's look at this model real quick to kind of get us thinking about it. Mr. and Mrs. Mason have 3 children. Assume the probability of having a baby girl is 0.5. And assume the probability of having a baby boy is also 0.5. As in, when you have a baby, you say 50-50 shot, right? Okay. Now, there's a model A here and a model B. 2 totally different things. A asks which model represents the situation correctly. Model A or model B?
Model B, because it looks more complex.
Model B because it looks more complex.
So the answer is either B or C.
Right on either.
Yeah.
What'd you say?
The math isn't mapping right on either.
Well, I mean, there's no boys on the other one.
Okay.
Oh,
Does it make sense that it's equal probability that you're going to have 3 girls, 2 girls, 1 girl, no girl?
No.
No, not really.
Exactly.
Right here, the more complicated one, as
That's
he
what I was
says.
thinking. That's
Okay.
I was just letting you.
It looks
Look at what's going on.
Right, that's
Okay? Think about this tree diagram. Okay? Your first child. It's going to either be a girl or a boy.
Oh, I was like, already.
Say you have a girl. Then what? What could your second child be? A girl or a boy. Say you had a girl the first child and a girl the second child. What could your third child be?
Girl.
Girl or
B.
boy. Okay? And you can do this with each of them.
Oh,
Okay? So then this off to the side says, okay, this top set is doing girl, girl, girl. This next one is girl, girl, boy. So 2 girls. We could go girl, boy, girl, 2 girls, girl, boy, boy, 1 girl. And there's a similar setup down below with the boys. Okay? So, which model represents the situation correctly? And that is model B. Okay? Each baby is an independent event, and not all options are equal, as shown in A. So,
each baby is independent.
yeah, each baby is independent, as in, does what you had as your first baby affect what you're going to have as your second baby? No. Okay. So each baby is an independent event. We'll talk about that word a lot today. And not all options are equal, as shown in A. Because A made it think it's equal for all of them. So, not all options equal, as shown in A. Okay, B. What's the probability that Mr. and Mrs. Mason have 3 girls?
1/8.
Actually,
How many options do we have here that have 3 girls?
1,
Just 1 out of
8.
8 possible combos.
12.5%.
So 1/8 you could say. You could say the decimal 0.125, or you could say 12.5%. Right? I don't think I have to cover the conversions. We've got that, been there, done that. C. Compare the probability that the Masons' first child was a boy, and then they had 2 girls, to the probability that their first 2 children were girls, and then they had a boy. Does the order affect the probabilities? So look at what we're talking about. First child was a boy, and then they had 2 girls. So that would be boy, Girl, girl. Okay, that's my abbreviation. Compared to, first two were girls, and then they had the boy. So girl, girl, boy. In both situations, we're looking at two girls, yes? So, what's the probability that it went boy, girl, girl?
1/8.
Boy, girl, girl. Any others that go boy, girl, girl? No, that's right there. So that is 1 out of 8 chances. What's the possibility, or what's the probability that it was girl, girl, boy?
1/8.
So girl, girl, boy. And that is also 1/8, yes? So, does the order affect the probabilities?
No.
No. Okay. Order does not affect the probabilities. And that has to do with every time you have a baby, the probability of boy versus girl is 1/2. Okay. And so that would be 1/2.
It's not.
1/2 for the first baby, times 1/2 for the second baby, times 1/2 for the third baby. Okay, so order does not make a difference because each probability is 1/2. Does not make a difference because each probability is 1/2, talking about boy versus girl there. So, if we're looking at probability that the first child will be a girl, that is going to be 1/2. Probability the second child will be a girl, 1/2. Probably the third child will be a girl, 1/2. It's going to be 1/8. 1/2 times 1/2 times 1/2, or 1/8, either way you go about it. Okay? Now, why did I start with this? I'm trying to get you to think of the distribution, how the pieces are distributed, how the probability is split up there. There's a few definitions in the middle of the page there. Okay? One definition is sample space. A sample space is a set of all possible outcomes of a situation or experiment. All of these combinations, girl, 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 boy, boy, girl, so on and so forth. That is your sample space, okay? All the different possible arrangements of answers. That is your sample space, so all possible outcomes. The other definition there, probability distribution, which is what we're getting ready to look at in this next one. Probability distribution for an experiment is a function that assigns a probability to each outcome of a sample space for the experiment. So the idea that each item that could happen has an assigned probability to it. How is that probability split up or distributed? Okay, and it'll make a little bit more sense after we talk about this one here. Okay, so let's talk about Tio and Henry. Tio and Henry are running for president of the student council. You will select a campaign button at random from the box containing 3 Tio buttons and 3 Henry buttons. You'll record the number of Tio buttons that you get. What is the theoretical probability distribution for the sample space 0, 1? Now, the key here is to understand what they mean by 0, 1. Okay? And notice here, sample space 0, 1 represents how many Tio buttons you can select in one trial. So, when you're pulling a button out of that box, it could be a Tio button, yes, or it could Henry. In other words, in respect to the question is about Tio, because we're recording the number of Tio buttons we get, it could be a Tio button or it could be a not a Tio button. Now, if it's not a Tio button, that's going to be represented as 0, because how many Tio buttons did you get? 0. If it's a 1, that's going to be represented as you did get a TO button, and so 1. And so so probability of no TO button, they represent as the probability of 0. So the probability of getting 0 TO buttons. Or the other option is the probability of getting a TO button. And the probability of getting a TO button is the probability of 1. Okay, so we're turning this into 2 options. Either you get a TO button or you didn't. Okay? Now, look at each of these probabilities. What is the probability of 0? So what is the probability that you got no TO buttons?
50%.
Could we say 50%? How many buttons are you drawing from?
6.
You're drawing from 6. How many of these buttons are not TO buttons?
3, 6.
3. In other words, how many are Henry buttons is basically what it's saying, right? And that's 3. And what do you know about 3/6? I have it as 1/2 on mine. Now, what's the probability of 1? So what's the probability of success? Or what's the probability of drawing a TO button? How many choices are there again? 6.
6.
Of those 6 choices, how many chances are there of getting a TO button? 3. So it is also 3/6, which reduces to 1/2. So when it's asking us for the probability distribution, it's asking us to tell them that the probability of 0 is 1/2 and the probability of 1 is 1/2. Okay, because it's probability distribution. How is the probability split up between 0 and 1? And so basically what we're saying here is it's a 50-50 shot, yes?
Yes.
You could get TO, you could not get a TO button. Does that make a little bit of sense? And I do think it'll make a little bit more sense when we put B with it, because I think it'll start to come together a little bit. B asks us, now you select a button at random, you put it back in the box, and you select another button at random. So now you're selecting 2 buttons, right? You'll record the total number of times that you get a, what are we talking about again? It's all about TO here. Okay, and record the number of times you get a TO button in the experiment. Define the theoretical probability distribution for the sample space, this time 0, 1, 2. And how's this probability differ from part A? So 0, 1, 2. 0 means you get no TO buttons. 1 means you get 1 TO button, one of your 2 draws. And 2 means you get 2 TO buttons, like both draws are TO buttons. Now, maybe you can see that and you know exactly what we're going for. Personally, make sure everyone gets there. I'm going to set up a tree diagram. First time you draw a button, what are your options? Okay, TO or not TO. Or for the purpose of this, I'm going to say TO or Henry, just because it'll be easier to acknowledge here. Okay, so you draw that TO or Henry button, you put it back, and now you're drawing another one. If you got TO the first time, what could you get the second time?
TO.
You could get TO again, or you could get Henry again, or Henry. If you got Henry the first time, what can I get the second time?
TO or Henry.
You can get TO, you can get Henry. Now, so what are those possible choices that we're looking at? The first option was you could get
2 TO.
TO twice. The next option,
No TO.
you could get TO and then Henry. Okay, down here, we could get Henry then TO. And the bottom option, Henry, Henry. Okay. With that in mind, Those are my options here. Probability of 0. Disagree?
It's going up a lot.
We've got a new setup here. What's the probability of 0? Probability of 0 means getting
None.
no TO buttons. How many of these options offer no TO buttons?
1.
Right here, yes. That's 0 TO buttons. That's one option out of how many?
4.
4. Are you with me on the 1/4?
Yes.
What about everybody else?
Yes.
Now, it also asked about the probability of 1. So, how many of my options involve getting a TO button once? Well, which ones include that? TO Henry or Henry TO. So that is 2 options out of 4, or as she said, 1/2. Probability of 2. What's 2 mean? 2 TO buttons. How many TO buttons do we have? There's one option up here, which is 2 TOs. So that's one option out of 4. Or in other words, 1/4. So my probability distribution is right there. Now, there was a follow-up question here. How does this probability distribution differ from Part A?
Well, you have a choice. Not 50-50 anymore.
Okay.
We're adding another graph. I don't know. How would you want to say?
What else? When you look at these distributions here, the results of these distributions,
They're all the same. You're equally as likely to get 2 TO buttons as you're going to get none.
so as
One is the same.
what?
One is the same, but one is different.
Okay, and the one we just did, we had 2 the same and 1 different, yes?
Yes.
What about Part A?
Both
Both
the
the
same.
same.
They were the same, yes? Okay, what I need you to identify here is that in this one, this probability distribution was, I'm going to use the word uniform because it is split up evenly. Okay, so you'll see the word uniform. Uniform, because it's uniform, it's split up into equal pieces there. So your probability is evenly distributed. As opposed to B, I'm going to use just the opposite of uniform being not uniform. It's not uniform because the pieces are not evenly distributed. Okay? Now, if you look in both cases, I don't know if you caught this or not, in both cases, my probabilities all add to be 1. And that will be true of any probability distribution. Your probabilities will add to be 1. Okay? So a uniform probability distribution assigns the same probability to each outcome. Okay. Now, top of the next page. I would love to take the time and talk about the red and green marbles. However, I'm going to be pushing it to get through just each topic once. So, I will leave a video later tonight. I will put the red and green marble example in my video. Okay, so you go back and get that, look in the video to get it later. We're going to talk in this section about developing an experimental probability distribution. Okay, so similar to what we were just doing, that we're looking at probabilities, but there's a little bit more to it. So, a cell phone company surveyed 500 households about the number of smartphones that they have that are in use. Would you recommend that the company concentrate on selling data plans for individuals or plans for families with 3 or more smartphones? So our job is to look at the data and decide where's our focus. Where are we going to get more of the people? Okay? So, Step 1, ask us to find the experimental probability. Okay, so we're looking at the probability of each one by finding each relative frequency. So look at this chart. This chart is saying number of smartphones per household. 0 smartphones per household has a frequency of 10, which means in this survey it happened 10 times. 1 smartphone per household happened 66 times. All the way up to 6 or more smartphones per household happened 44 times. That's what frequency is. How many times did it happen? The relative frequency is basically finding the probability of each one. So relative frequency. Okay. I'm going to start with these as fractions. You'll need to calculate your sides. We're going to turn them to decimals and percents. Ultimately, I work with this problem in percents. We just have to get there. So, 0 smartphones per household happened how many times? 10. Out of how many households were surveyed? 500. So 10 out of 500 had 0 households. What is 10 divided by 500? 0.02, which is what is a percent? 2%. We're going to go through and do this on each one. 1 smartphone happened in how many households? 66 out of how many? 500. 66 divided by 500 is... Okay. And I have them each listed as 3 decimal places, but then when I turn them to a percent, I have them as whole percents. So 0.132, move your decimal to right, 13.2%, or what I'm going to write is 13%. Okay, 2 smartphones, 120 times out of 500. Divide it, 0.24, 24%. Okay. 3 smartphones, 144 times out of 500. 0.288 is what I have written down, which becomes 28.8%, but rounds to be 29%. 4 phones happens 79 out of 500 times. 0.158, which is 16%. 5 phones, 37 out of 500 households. 0.074, which is about 7%. And 44 out of 500 cell phones. 0.088, which is approximately 9% here. Okay, that was finding each relative frequency. So looking at the fractions and changing them to decimals and percents. Okay, this is our probability distribution, folks. If you add these up, guess what? All these percents are going to add to 100%. And I think they actually do add to 100%. It could get slightly off in a rounding situation, but generally speaking, 100%. Now, 2 ask us to graph it. So along the left, we have the probability. Along the bottom, we're going to have smartphones per household. So I'm going to have a column for each. We're just going to do a bar graph. So 0, 1, 2, 3, 4, 5. And I'm calling my last one 6 plus, or 6 or more. And this is smartphones per household. Okay. So, 0 smartphones. What percent? It was 2%. So I'm just making a bar. I'm not having these bars touch. But there's my approximate 2% bar. I mean, it's not a histogram, it's a bar graph, so they don't necessarily usually touch, but it doesn't matter for what we're doing. Okay, 1 smartphone, 13%. Again, just ballpark it, folks. 2 smartphones, 24%. 3 smartphones, 29%. What we're doing, we're getting a visual here. 4 smartphones, 16%. Ooh, that was. Five smartphones, 7%. And 6 smartphones, or 6 or more, 9%. Okay, guys. There's what you're looking at. Now, our job is to answer the original question. Okay? The bar graph allows us to be able to view it a little bit easier. Okay? Would you recommend that the company concentrate on selling data plans for individuals or plans for families with 3 or more smartphones? How can we figure this out?
See which has the bigger proportion.
Okay.
Ratio.
See which has the bigger amount. In other words, what is it? It's 3 or more, right? Families with 3 or more. What would the others be? Less than 3. Okay. So if we look at probabilities of families with less than 3 versus probabilities of families with 3 or more. What do we know about families with less than 3? What is that? That means they have either 0, 1, or 2 smartphones. And what are those percents?
2%, 3%, 75%.
2%, 13%, and 24%, which total to be 39%. Well, that kind of tells me right there where I'm going to land. Families with 3 or more smartphones. What percents are we looking at there?
16.
29, 16, 7, and 9, which totals to be 61%. Okay? So, where's the company going to find more business? Should they market to family plans or individual plans? Family plans, yes?
Yes.
They're going to have more business selling the bigger plans. Okay? You guys can probably each attest to that if you think about how many smartphones are in your household, right? Okay? It's a common thing these days. So, family plans, since 61% of households have 3 or more smartphones. Family plans, since 61% of households have 3 or more smartphones. Okay. Top of the next page talks about drama club. I'm skipping that example because it matches up with this one. Okay, I'll include it in a later video. Okay, I need to take a few minutes to talk about binomial experiments, which is the next piece here. Okay. Binomial experiments. Okay. A binomial experiment is an experiment that consists of a fixed number of trials with the following features. So one of the things we're going to do here is decide what's a binomial experiment, what's not a binomial experiment. If it is a binomial experiment, it must meet these three qualifications. Okay? Each trial has to have two possible outcomes. One which is deemed as or denoted as success. The other is just usually everything else, okay? Not doing that. The second thing, the results of the trials are independent events. One event cannot affect the other if it's a binomial experiment. And third thing, the probability of success is the same for every trial. In other words, you're looking for uniform. Okay? So, with that in mind, easiest thing for me to do is to go through and kind of take you through an example. Okay? So, the question is it a binomial experiment? This spinner is spun 3 times. Assume that the spinner is equally likely to stop in any of the sections, so it's a fair spinner basically. Success is landing on a section marked go forward 2 spaces. Okay, that's what success is. So, first thing, if it's binomial experiment, there are 2 outcomes. The success, and then the rest. Are there 2 outcomes here? What is success? Go forward 2 spaces, that's success. If that is success, that means everything else is
Failure.
the failure, okay, or the other thing. So, are there 2 outcomes?
Yeah.
Success of go forward 2 spaces, or
Everything.
not landing on go forward 2 spaces. So I'm going to say 2 outcomes. Go forward 2 spaces is 1 outcome. Or the other one is, I'm going to say, not landing on those spaces. So basically landing anywhere else. But that's considered 2 outcomes. Landing in the place of interest or landing elsewhere. So do we have 2 outcomes? We'll say yes. Okay, so 2 possible outcomes. Second thing to check. Are they independent events?
Yes.
What do you know about spinning a spinner? One spin of a spinner has nothing to do with the next spin of the spinner, right? So it is independent. One spin does not affect the next. So the question was about independence. So independent, one spin does not affect the next. Okay, so independent. And third one, probability of success is the same for every trial. So, and this kind of has to do with independence, okay? What is probability of success? In this case, success is
Go forward 2.
go forward 2. So probability of go forward 2. What's the probability of go forward 2?
1, 2.
2/8, which reduces to 1/4. Is that going to be the same next time you spin the wheel?
Yeah.
Yeah. You don't get to remove that spot after you land on it or anything, do you? It's still a spot you can land on. So, is it going to be 1/4 each time?
No.
Probability of landing on go forward 2 spaces is going to be 1/4 each time. So is it equal probability? Yeah, because each spin is independent of the next. I just checked 3 boxes essentially. So what am I saying?
It is a binomial.
Yeah, this is, I'll put it over here because I ran out of room over there, a binomial experiment. Okay. We checked all 3, we were able to check all 3 pieces, so we were able to say it is a binomial experiment. Now, B. We're going to consider, is this one a binomial experiment? In a class of 23 students, 7 students completed the term project, 2 students selected at random have to give presentation. Success is that the student has completed the project. Well, we're going to talk about 2 outcomes, first of all. In other words, I'm checking all my check boxes. Are there 2 outcomes?
Yes.
Success is a student has completed the project. So the opposite of success in this case is not completed the project. So are there 2 outcomes?
Yes.
Yeah. They either completed or did not complete the project. Okay, so we can check the first checkbox. There are 2 outcomes. Now, the results of the trials are independent events.
They're not independent.
Okay, well, what's the probability that the first person, so success is they've completed the project. What's the probability the first person has completed the project?
7.
7. There's 7 students that have completed it out of 23 students being picked. Now, what's the key here? Yeah. You just picked one person to present their project. Are they still in this pool when we draw the second person?
No.
No. Now we're only picking from 22, and if we're assuming they've completed their project, 6. What is that showing right there? Are 7 out of 23 and 6 out of 22 the same? No. So right there, are these independent? No, they're not. They're not independent because we had to change our number here. It's not independent, and what's the other one? Is the probability of success the same for every trial? No. Okay, so this one, they're not independent and not equal probabilities. Not independent and not equal probability. So at this point, we failed check boxes 2 and 3. Am I making sense?
Yes.
So since I failed check boxes 2 and 3, this is not a binomial experiment. Okay, so kind of look through those check boxes to think your way through. Now, hear me out. The top of the next page, I didn't need to do the additional example. My failure today, I didn't get to the binomial probability formula. Okay, that is my failure today of what I haven't reached. It will be in the video. I may even do a separate video just on that. I don't know. We'll see how today goes. The formula I did not get to is this right here. Okay. Now, for a binomial experiment consisting of n trials with the probability of success p for each trial, probability exactly r successes out of n trials is given by this formula. NCR. We know NCR, yes?
Yes.
Okay. P stands for probability. So p raised to the r.
Yes.
And 1 minus p to the n minus r. You're familiar with those variables. I'll talk it through on the video in an example. Okay? Tomorrow, you have lots to get done. Get your notes done. Get your syllabus done. Okay? So you have more really than what you're going to be able to do in a period, to be honest. Okay, so you're gonna have to do a little bit of homework somehow or another. So plan accordingly. The video, I would love to say it would be on early, but it may be after the softball game tonight. So, gotta do my daughter's softball game, which makes it late. And I will get Savas opened up here later too.
Have a good day.
Behave tomorrow, please.